Well, this is going to be a quick and I hope painless review of Week 9, Class 1, in which we started talking about why feedback. And I asked everybody to watch a 20-minute video of what I think are the most important concepts that we should take away from Arrow 320 and 420 when taken together. And also to consider a short 5-minute segment from minutes 5 through 10 of a lecture by Gunther Stein in 1989, which explains how control can get out of control. We could have preventable control catastrophes if we forget 3 easy facts. And if you put those facts in RC7, you'll get 10 points. All right, with that introduction then, for the last 2 weeks, we're going to talk today about getting transfer functions from experimental data. And comes from NASA Ames, called Cypher, developed by Mark Tischler, and which is sold and taught to industry a few times a year. We're going to do it by hand today. And what it presumes that somehow you get an experimental transfer function from a system. Now, this might come from a wind tunnel. It might come from a flyable system that you put in what's called a chirp input, a sinusoid input into the pilot stick, covering many frequencies, and then over a limited frequency range you'll get this transfer function output. So can we build a control system that will work if this is our controlled variable in our Bodhi plot variable? And can we build a control system just from the frequency response that comes experimentally? Which the answer is yeah, you can do it. And here's an example of a Bodhi plot where all we need to do is find a low frequency asymptotic gain and then go from left to right, matching asymptotes for gain and phase, and then trying to fit the transfer function. And actually it's not very difficult at all to get close, even by hand. Of course, by computer, it's done relatively rapidly. But let's do this first one by hand. So here is the actual Bodhi plot. And we can see that it's got a flat low frequency gain of minus 24 dB. And if we were to convert that to gain, you'd say 20 log gain equals minus 24. So log gain would be equal to minus 24 over 20, which is minus 1.2. And 10 to the minus 1.2 gives you a magnitude of 0.0631, or 1 over 15.8. So if we raise this thing by a gain of 15.8, we'd get up to 0 dB, up to 1. We see the phase angle starts at 0. So we assume that there's just a constant gain at low frequency equal to 1 over 15.8. Then I notice that there's a bump, which would indicate a possible resonance or a second order term. And it looks like it goes up about 6 dB. So if it was a second order term, then I would go from 0 phase at low frequency to 180 degrees at high frequency, which is exactly what happens. And this slope of the after resonance turns out to be, looks like 40 dB per decade, 10, 20, 30, 40 dB per decade. And so that indicates a type 2 system with a resonance peak right here. And the break looks like it occurs at 5, 4, 3, 2, 1, yeah, 5. So the omega n is 5. And the rule of thumb for the zeta is it's 1 over the peak. Its damping is 1 over the peak. So we have 6 dB peak from the low frequency to the high peak. So 1/6 would give us a damping of 0.17. So with that, I think I can take a pretty good stab at what this transfer function is. Put that transfer function into a function called g Bodhi, a variable called g Bodhi, and here's my gain, and then it's over s squared over 25 plus 2 zeta over omega n times s plus 1. And that gives me my second order transfer function with damping of 0.17 and omega n of 5. So we'll go ahead and then call the Bode plot for that, G Bode, and there it is. And then I'll put hold on and look at the actual Bode plot, that was our original transfer function, and we'll take a look and see what it looks like. And that's not too bad. So we have a couple observations here. The low frequency gain is a good match, and I see that I'm too short on the peak, so I might want to reduce that damping from 0.17 to something lower. I also missed out on the high frequency asymptote, so that needs to be looked at. But the easiest thing to fix, though, is over here at the phase, because I see that my phase starts dropping off on the estimated Bode plot at around 0.2. So what would cause that would be a pole at 2. So here's 1, 2. If there was a pole at 2, then the phase would start dropping off at 0.2. And so I'm going to guess that there's a pole or something acting like a pole at 2. But this angle doesn't become 90 degrees. If it was simply a pole and only a pole, then this angle would go to 90 degrees, and the final high frequency asymptote angle would be minus 270 and not minus 180. So something must pull it back again. So something between 2 and 6 possibly is 0. And that 0, of course, would change my HFA a little bit also. So I'm going to guess that there's a pole at 2 and a 0 at 4. Just a guess to throw that in and see what happens. So here in MATLAB, I've added my s over 4 plus 1 divided by s over 2 plus 1. And again, you use this format for the Bode plot because then you see that the LFA, the low frequency, is 0 dB. So anything to the left of this is not going to change the gain. So I have a pole at 2 and a 0 at 4. And then I take that G fix and I'm going to add it to G Bode. So we'll say that G Bode new equals G fix times G Bode, like so, and then we'll Bode plot that, G Bode new, and there's G Bode new, and then we'll put hold on again, and then we'll Bode plot the original transfer function from experimental data, and I see now that I've got a pretty good fit. Got a good fit. The peak looks like it's nice. I'm missing a little bit on the HFA, so I probably missed the location of the 0 or of the pole by amount. But you can see that I'm almost overplotting this thing. So here I have a simple fit to a transfer function, which gives me, when I'm done, a transfer function shown here, which I call G Bode new. And it's 0.8 times s plus 4 over s plus 2 in a second order term with damping at 0.17 and a natural frequency at 5. Now here's the thing. I really only need to match at crossover. That's the crucial place for me to match. So on my transfer function, as long as I'm matching, assuming that I'm going to put my bandwidth somewhere over here and raise the gain, if I'm going to do that to the Bode plot, then I'm going to want this area here to be a good match. So, from this experimental data or the transfer function fit, if I were to review what I did last week, or what we did in class last week, if I wanted to make the bandwidth 10 here, I would raise the gain. It looks like 40 dB. I'd raise the gain, and that would make this point the crossover frequency. And I see I have a very low phase margin. I'm guessing 15 or 20 degrees of phase margin, way too low. So I would put a passive lead compensator to give myself at least 45 degrees at that location. And since that's at 10, the passive lead compensator would have a 0 at 10 and a pole at 100. So I would add a passive lead compensator of s over 10 plus 1 divided by S over 100 plus 1, and that would give me my crossover frequency of 10 with the 50 or 60 degrees phase margin. So let's go ahead and try that really quick. So here I've added my G lead, break frequencies at 10 in the numerator and 100 in the denominator. And then I've multiplied my OLTF times that G lead. And so we can SISO tool that OLTF1 and take a look and see how it looks. So we'll just raise the gain when this thing finishes. Yeah, there's a decent step response. So for a first cut, that's not bad. But so this is not following a step input. It's 0.8. It's too low. Let's take a look at the Bode plot and see how I can fix that steady state error. The steady state error comes because it's a type 0 system. Type 0 system means that the low frequency asymptote is constant or flat, a pure gain. And we saw back when we started this thing that the pure gain was going to be 1 over 15.8. So we need to have high gain at low frequency. Now I'm going to go back to the video that I've asked you to look at right now, in fact, if you don't understand what I just said. The reason I want high gain at low frequency is because loop shaping should give me a system that looks like this. High gain at low frequency, which is low frequency means below bandwidth, below crossover. And low gain at high frequency means a rapid roll-off. Well, our system is flat here, and that's why we're not following a step input. So if I put an integrator into the lower portion of this root, if I put an integrator, then the low frequency gain would go to infinity, right? So why wouldn't I just do that? I'll just put an integrator that operates over here, add it, and we'll call that a integral lag compensator, and put it in here. Well, some of you might say, well, wait a second, the integrator is going to have 90 degrees of phase loss. So if I have 90 degrees of phase loss, then my phase margin will be destroyed. If I have 45 degrees of phase margin here, the 90 degrees is going to give me minus. It's going to drive the system unstable. The integral itself will drive the system unstable. So I have to put the integrator in, but take the phase loss out. And I do that by what's called an integral lag compensator. So here I have computed an integral lag compensator of s plus 1 over s. And you might ask, well, why did you pick 1? Well, because the 90 degrees of phase that comes from the s plus 1 term is going to start at 1/10 of 1, or omega equals 0.1, and the 90 degrees is going to completely be added at 10 times 1, or at 10. So that's my crossover frequency. So if I add the s plus 1 over s, the 90 degrees of phase loss from the denominator will be taken out at 10, which is the bandwidth. So my phase margin won't change. So let's just take a look and see what that would look like. Here's the asymptotic plot for the integral lag compensator, s plus 1 over s. And you can see my LFA, my low frequency asymptote for s plus 1 over s is simply going to be 1 over s, which is shown here. The angle, however, is going to start at 0.1, and it's going to take my angle is going to increase by 90 degrees from 0.1 to 10. Right? So the low frequency asymptote of minus 90 degrees from the pure integrator is going to be taken out from 0.1 to 10 by the s plus 1 in the numerator. Now don't forget, I'm going to add this. I'm going to add these curves onto the old Bode plot. So do you see that I'll be adding high gain at low frequency without changing crossover? I won't change anything at the crossover point over here because the angle will be 0 by the time it gets to crossover. So let's see how that works. So here's the integral lag compensator, s plus 1 over s. And there's my open loop transfer function which is the Bode plot transfer function that I computed, plus the passive lead, which is s plus 10 over s plus 100. So now we're going to multiply the integral lag times the transfer function and get our second open loop transfer function, which will be seen here. And now we can SISO tool that. We call that OLTF2. We'll let this guy run. And now I can see if I get my bandwidth of 10 that I wanted, my phase margin is 43 degrees, and look at the slope on the left-hand side. Look at the slope. So now I would expect that I would, since that's a type 1 system now, we know that a type 1 system will follow a step with no error. And we see certainly there it is. I've got no error in my type 1 system. I've got some oscillations I may want to play with and iteratively take out by moving the poles and zeros around. But basically, I've got a design that would meet specifications here. Now, one thing to emphasize here, I'd like to emphasize this. I've used the root locus just to make sure my roots are okay. And look at the roots tell me I can actually raise the gain maybe a little bit and get my damping up there. So it looks like I could raise the gain over here and make this a 1112 bandwidth system, increase to 54, 60 degrees of phase margin. I could even go a little bit more than I want. Make this around 60 degrees of phase margin, and hopefully that would even get to be a little better system. Yeah, look at that. So I could increase the bandwidth by looking at the root locus. I could increase the bandwidth and actually get rid of that oscillation in my system and have a really nice response. So this is the power of SISO tool. We got our bandwidth from the passive lead compensator with the phase margin, and then we modified with the integral lag compensator the low frequency part of the curve to give us a type 1 system. And notice now, it didn't matter what G was, what the plant was. Once I made it a type 1 system, it didn't matter what G was. It was going to make my output equal to my input, period. Now I might have different dynamics because of the crossover behavior. But the crucial thing was that we modeled the correct behavior at crossover separately from what I did to the low frequency part of the curve. Now if I have noise out here at high frequency and I needed to attenuate that, I would just put a filter out here, say S plus 100 cubed. And S plus 100 cubed would roll this thing off rapidly. Why 100? Well, the phase angle from 100 will start to affect this gain curve at 10. And 10 is my bandwidth. So go ahead, affect my gain curve at 10. I don't care. But if I made it S plus 50, if I made it S plus 50 cubed, then the phase curve would start to be degraded at 5. And so that would reduce my phase margin. So that's how you do the thinking with this thing called loop shaping. And you can see the loop shaping here that we ended up with the phase margin kind of closely matches what the video said we should look for. If this is a good open loop system, then it looks like we kind of got that. And then we can expect a good closed loop system at a bandwidth equal to crossover, or near crossover, if we get this kind of a loop shape. So, does this work? This technique works 90% of the time. What will throw this technique off? Well, right half plane zeros might not make this technique work, right? Because you know if you raise gain enough with a right half plane zero, you're going to get the root locus over there, and that's going to screw up your phase curve anyway. The right half plane zero will cause a change in direction of how the phase works, as will an unstable pole. So if we had a highly unstable pole, we would have to first get our SAS loop to get rid of that unstable pole. We can't get rid of the unstable zero. We can get rid of the unstable pole by our first loop closure, and then apply this technique to the second or outer loop closure where it will work. If this technique does not work at all, then you should have caution and go back and look at those 3 facts that you don't want to violate for these systems so that you don't have a catastrophe on your hands. Gunther Stein talks about those 3 facts. That's the end of what we did today. I should point out one final thing. This is the original Bode plot, the experimental Bode plot. And do you see that there really was no need to fit the transfer function to it? I could design right to the gain and the phase curve. In fact, often people will just design to the gain curve. They'll just design to the gain curve and at crossover get their 20 dB per decade and assume that if they're minus 20 dB per decade near crossover, that their phase margin is tending towards 90 degrees. You see that? So a really good control designer using loop shape can loop shape off the experimental gain curve alone. Now again, it may not work if he has a right half plane 0 or an instability in his system. Right? That may not work. But if he has a minimum phase system, it should work like a champ. So that ends what we did today. We'll pick up the effects of time delay tomorrow.